for this first part of the question, you can see it's asking for the type of nucleon, two different types within this americium-241 nucleus. Now, the nucleus is obviously going to contain protons and neutrons, so we need to know the number of each of those, essentially. So the first thing to note from the two numbers at the top here is that the 95, the lower number, is the number of protons. If we write that down first of all, so type of nucleon, proton, and there are 95 of those. Now, to get the second mark, we need to identify the number of neutrons, which is going to be this bigger number minus the number of protons. The bigger number represents the number of protons and neutrons. So if I just write that in there, 241 minus 95 is going to give us 146. So there are 146 neutrons in that nucleus, and those are your 2 marks there. So for this second part of the question, it's asking to state the decay process responsible for turning americium-241 into plutonium-241. You'll notice that the element itself has changed, which means that the number of protons has changed. As you can see, it's gone from 95 to 94. What we can identify from that then is that beta minus decay must have occurred. So this is the first mark in the question. And it's very important that you identify it as beta minus decay because beta plus decay would give you a different balance of charge and it wouldn't quite work in the same way. Now, you could, if you wanted to, write out this equation just to confirm that mark and show that you understand what's going on. But basically, where the number of neutrons hasn't changed, but the number of protons has, that's how we identify it as a beta decay. In order for the number of protons to go down, what we're saying there is that we've lost for this part of the question, we can see that plutonium-241 is decaying to form americium-241. Now, in that process, we are gaining a proton, we're gaining a positive charge, and in order to balance that charge, there must have been a loss of negative charge. Gain in positivity, loss of negativity. So that tells us that it is a beta minus charge, a beta minus decay. Now, as is the case with any beta decay, there is no change in the overall mass or the overall number of nucleons. So what I'm going to say here also is that the overall nuclear mass does not change. And those are your 2 marks there. Very important to say that it is beta minus decay, as you may not get that first mark. In this next part of the question, we've got an americium-241 nucleus, which is decaying into nuclide X by emitting an alpha particle. So we want an equation for the decay of that nucleus, and therefore the proton number and the nucleon number of X at the end. So as with any alpha decay, the first thing we want to do is write in one of the common products, which means there's always going to be a helium nucleus produced. So we're going to end up with some nuclide X. We just work backwards here. Americium-241, as you can see up here, looks like this. If you're not sure what that would look like in the symbol equation, you can see it's 241 AM95. So let's just write that in. So 241. Without a periodic table, we're not going to know what that element is. So if we just leave that as X for now, the thing that we're interested in is actually balancing the number on the top and the number on the bottom. So a helium nucleus is released. So there are 4 nucleons released from this 241. So if we do 241 minus 4, we're going to end up with 237. And if we do 95 minus 2, which is the number of protons, we are going to end up with 93. So whatever our nuclide is, those are the resulting numbers. So we just write those in at the top, at the bottom. A materials question now, and one that's got quite a few parts contained within it, some of which actually link together, but we'll get to those questions. First thing we need to do is just read through the introduction and just pick out any key bits of information that might come in useful later. So a student adds a series of masses to a vertical metal wire of circular cross-section. Now that's important, first of all, because when we're working at cross-sectional area for an object, then we're going to know that where it's a circle, we can use area equals pi r squared for that. So we'll come to that later. And measures the extension of the wire produced. Figure 1 is a force extension graph of the data, and then it gives you that graph there. Now, the first part it says is to mark on figure 1 the point P, the limit beyond which Hooke's law is no longer obeyed. Now, looking at this, we can see actually that Hooke's law region is the straight line part of the graph, because Hooke's law is where the force is proportional to the extension. So the limit at which that's no longer the case, obviously the point where it's no longer a straight line is just at the top here. So just that point P. Outline how the student can use these results and other measurements to determine the Young modulus of the wire. So we're going to use the Young modulus equation, but we're going to modify it slightly. So I'm going to use a capital Y to represent the Young modulus first of all. And I've written that Y is equal to sigma divided by epsilon. Now sigma is the stress, which is force divided by area. Force divided by cross-sectional area, remember we looked at that before, and epsilon is the strain on the material, which is equal to extension x divided by original length L. So we're going to combine those second two equations, the second and third equation, together and substitute them into the Young modulus equation so that it should look like this. Now, the marks in this question are going to be obtained by correctly substituting in everything into that equation, because there is one more modification that we need to make. You also need to talk about what those other measurements are that we need to make. So we can actually work that out from this equation. Now, the first thing to say is that actually we don't know the original length, so that's a measurement that would need to be taken. What you'd also want to say is that you want to measure the diameter of the wire, and we'll talk about that in a second. Now, because this wire has a circular cross-section, we can not only say that the area is equal to pi r squared, but it's also equal to pi times half the diameter squared. So we can substitute that into the equation as well. Now, you might be wondering, well, how do we use the graph to obtain any data here? Now, what we can do is bear in mind that the gradient of the straight line region is going to be the force divided by the extension. If I just show you that on the graph again. So force divided by extension, we can find the gradient, change in y divided by change in x. So what we can say here is where we can take f and x out of this equation, we can rearrange it slightly. And then that agrees with our two earlier statements about measuring the length and the diameter, because those are the only two that are left in that expression after, in the expression that's multiplied by the gradient. So in terms of where the marks are obtained in this question, I would say that you'll get mark for correctly mentioning both of these. You get another mark for correctly writing out the equation in its final form. What you probably want to do also is write out in full that you need to find the gradient of the graph and what that represents. And then those are your 3 marks. When the wire has been extended to A, the masses are removed one by one and the extension remeasured. Draw on figure 1 the shape of the graph that the student will obtain. So what you need to bear in mind with this is that when you're unloading the material, when you're removing the forces, actually it continues to obey Hooke's law. We get a straight line that moves back. And you'll notice I've drawn that line parallel to the Hooke's law region to start with. What's happening there is that the forces between the individual atoms in the metal wire behave exactly the same as they do when the masses are being loaded. So actually it obeys Hooke's law on the way back. And that's actually what we're going to use to answer the next question. To explain why the graph has the shape that you have drawn, there are 2 things that we can say here. Firstly, we can mention plastic deformation. The second point that we can make is that we keep that same gradient on the unloading of the material because the bonds between the atoms behave in exactly the same way. So 2 points there, 2 marks to be obtained. The metal wire is used to make a cable of diameter 6 millimeters. The Young modulus of the metal of the cable is 2 times 10 to the 11 pascals. So essentially this question is going to be a case of inserting the values correctly into the equation and getting the correct value out. But you need to know how to do this properly. So let's take a look at that equation again. Now the thing to observe here is that actually we're given a strain value, not an extension and an original length. So we need to know exactly what to do with this 0.2%. Now the 0.2% is actually just a number, as is the strain value. Strain doesn't have a unit because it's a length divided by a length. So what we need to do is work out how to fit the strain into this equation. What you'll notice there is that I've taken the L and the X out, and actually L divided by X is the inverse of the strain because strain is X divided by L, and then the other values I put in an expression which is then multiplied by. So what we need to do here is to substitute the numbers in. Just bear in mind that the 6 millimeters, well, it's a value in millimeters, so we need to convert that to meters before putting it into the equation. We also need to rearrange the equation to make force the subject, so let's do that now. And you'll notice that instead of saying X divided by L, I've just written the epsilon, which represents the strain. So let's just write down what that strain actually is. So the strain is actually 2 times 10 to the power of minus 3. Remember, it's 0.2%, and 1% is 0.01. So let's substitute the values in. And that should give us a value of 11,300 newtons. So actually, when we convert that to kilonewtons, that's going to be 11.3. So for this question, we get 1 mark for correctly rearranging the equation and making the correct substitutions. Another mark for correctly substituting in the values. And a 3rd mark for getting the correct answer. Now, in some cases, you may wish to use the values that you're given here. You're given the Young modulus, you're given the strain. You could use that to work out the stress and then use that to work out the force. Remember, we've got these equations like Young modulus equals stress divided by strain, or stress equals force divided by cross-sectional area. You could do that, but it involves more steps, and in theory, you could end up doing more rounding, which might truncate your value more. But both methods are valid. The marks might be distributed slightly differently, but the way that I've outlined here is a perfectly fine way to do things. The cable is used in a crane to lift a mass of 600 kilograms. Determine the maximum acceleration. So acceleration, very important point there. with which the mass can be lifted if the strain in the cable is not to exceed 0.2%. Now, you might be looking at that and thinking, well, we've got a mass, we want to work out an acceleration. Let's lean towards F equals ma. Force equals mass times acceleration. Looking at the previous question, we can see that if the strain in the cable is not going to exceed 0.2%, then the force is not going to exceed 11.3 kilonewtons. So what we're actually saying there is that if the force on the cable is 11.3 kilonewtons and the mass is 600 kilograms, well, let's just work out an acceleration from that. It's actually not that simple, because remember, this F in this equation is the resultant force. So what we need to do first of all is draw a free body force diagram. And what I've done there is included the tension in the cable, which is 11,300 newtons, and the weight of the mass, which is going to be 600 kilograms times the gravitational field strength on Earth, which is 9.81 newtons per kilogram. So yes, we can use F equals ma, but we need to work out the resultant force first, which should be the difference between these two forces. If we rearrange this equation to make A the subject, we can then substitute in the fact that F is equal to T minus W, because T minus W would then be the difference between the two forces acting on that mass. And then it's just a case of correctly substituting in the values. And that should give us a value of 9 meters per second squared. Now, this is a rounded value, but you'll notice that any values that we've been given are to two significant figures. So we need to keep the answer consistent, and it needs to have the same number of significant figures as the least precise value in the question. So for this question, you'd get a mark for correctly identifying the weight of the mass and acknowledging that that needs to be factored in. You'd get another mark for correctly rearranging the F equals ma equation and making correct substitutions. And then finally, a third mark for getting the correct answer. So an engineer redesigns the crane to lift a load of 1,200 kilograms. Now that's the key point there. In order to do that, that same acceleration is going to need double the force. And let's just take a look at why that is. So I've said here that the resultant force is equal to the mass times acceleration, but it's also equal to the tension in the cable minus the weight. Now, if we rearrange that to make the tension the subject, because that's the thing that we're interested in. So the tension is equal to the resultant force plus the weight. Now let's look at what those, let's make some substitutions for the force and the weights. So I've said that F is equal to ma and W is equal to mg. I've then factorized that, so I've taken the ma and left the a and the g in brackets. So what we can see there is that by doubling this mass, we would actually need to double the tension. Now we're going to need to make those changes in the cable, which is what the question is asking for, in order to be able to have that double tension. Now let's look at our Young modulus equation again that relates to the tension. Now what I'm going to do here is instead of saying F, I'm going to say T, because actually it's not the resultant force in this equation, it's just the tension in the cable. It's the force that's trying to extend the cable itself. Now let's make the tension the subject again. And I've also written x over L as epsilon, so the strain again, like I did before. Now what you can see here is that actually we're interested in keeping the strain the same, but doubling the tension. So we need to work out what else we need to do to these other values, perhaps the value of y or the value of d, in order to make that happen. So as you can see, these values in the middle, this value of pi d times d over 2 squared y, overall, that value will need to double in order to meet that doubling tension. So here are the things that we can do. you can double the Young modulus. Now you can see there, if we want to double the value of pi times d over 2 squared y, we could just double the Young modulus, and that would multiply that whole expression by 2. You could also double the cross-sectional area, multiply that by 2. That would mean that for the diameter, you wouldn't need to double that because you're squaring up the diameter. So actually, you'd only need to increase the diameter by √2. But if you said double the diameter of the wire, that's also fine. So those are the two only changes that we can make because those are the only two variables that appear in that expression that we're multiplying by 2. So in terms of where we would obtain the marks, you get your first mark from correctly writing down this resultant force equation and then identifying the fact that doubling the mass requires double the force. You would get another mark for saying to double the Young modulus, and then your third mark for suggesting about doubling the cross-sectional area or doubling the diameter. So 3 marks there. So now we're on to a question on electrical circuits. So let's have a look at what the question is asking for to start with. The cells in the circuit shown in figure 2 have zero internal resistance. Currents are in the directions shown by the arrows. So we can see these arrows down here that we're interested in. R1 is a variable resistor with a resistance that varies between 0 and 10 ohms. Now the first thing we need to do is write down the relationship between the currents I1, I2 and I3. So you can see I1, I2 and I3, I've highlighted the arrows, the directions of the currents there. For this question we need to use Kirchhoff's first law, which tells us that current is conserved across any junction. So what that means is that the sum of the currents going into the junction is equal to the sum of the currents leaving. So as we can see there, I1 and I2 are going in and I3 is going out. So what that will then mean then is that the sum of I1 and I2 is equal to I3. Now you could write that in a reordered way and still get the mark. For example, you could put the terms either side of the bracket, say I3 is equal to I1 plus I2. You could have, I don't know, I1 is equal to I3 minus I2 if you really wanted to, but I think that's overcomplicating things. They couldn't deny you the mark because it's still technically a correct relationship between those 3 currents. R1 is adjusted until it has a value of 0 ohms. State the potential difference across R3. Now, if we take a look back at where R1 is, so what we're saying there is that R1 is adjusted to the point where it's got 0 resistance. So actually, this resistor here may as well not be there because it's got 0 resistance. So it could just be a wire effectively. So we're interested in what effect that's going to have on the potential difference across R3. Now, according to Kirchhoff's second law, the PD potential difference in a closed loop, the net PD is going to be 0. The sum of the EMFs has to be equal to the sum of the PDs. So if we just write that down as well. So we can see that actually the potential difference across resistor 3 would therefore be 10 volts also. Determine the current I2. So let's have a look back at that diagram. So what we can see there is that on that basis, when the potential difference across R3 is 10 volts, if we look at Kirchhoff's second law again for the closed loop on the right, we can see that where there's an EMF supply of 12 volts, but R3 is taking 10 volts away, what's then remaining is going to be 2 volts. So let's write that down. We can then use V equals IR to work out the current through R2. So let's actually write that down in the question area. So as you can see, 0.2 amps. Now you would get a mark for correctly making that calculation and making the correct substitutions. What you probably want to do is write down that this 2 is equal to 12 minus 10, just so the examiner's aware of where you got that from. You could even write it out in full in that fraction, actually. So there's your first mark. And then the second mark would be for getting the correct answer. State and explain what happens to the potential difference across R2 as the resistance of R1 is gradually increased from 0. So we're interested in what happens to the potential difference across R2 over here as we bring this resistance of R1 back up from 0, because it started off as being 0 at the beginning of the question. So the first thing to note is that if this resistance is going up, it's going to take more energy out of the circuit, which means that the potential difference across R1 is going to increase. Now, if we are still going to obey Kirchhoff's second law, then of those 10 volts that are supplied to this closed loop on the left, fewer of those volts are going to be dissipated by resistor R3. So actually the potential difference across R3 will go down. The second thing that we want to note is that actually if the potential difference across R3 is going down, but we're keeping this 12 volts the same, then R3 takes a smaller share of the volts, which means that R2 is going to take a larger share. So actually the potential difference across R2 is going to increase. So let's find a way of putting that into words. So the first thing to note is that actually by increasing the resistance of R1, its PD will increase. The next thing to say is that R3 will take a smaller share of the PD in its closed loop, so actually the PD across R3 will decrease. With that being the case, it's also going to take a smaller share of PD in the right closed loop, and that will therefore mean that the potential difference across R2 is going to increase. And then those are your 3 marks, those 3 points. So we're now on to a question about momentum. What we've got here is an air rifle pellet that is shot into a block which is hanging from a string, and then we need to make some calculations surrounding that, ultimately determining the speed of the pellet. So let's just read through the question first of all. The speed of an air rifle pellet is measured by firing it into a wooden block suspended from a rigid support. The wooden block can swing freely at the end of a light, inextensible string. Now that's important because that tells us that if we're not extending the string, we're not storing any elastic potential energy in the string. It itself doesn't have any mass either. So all of that energy presumably is going to go into kinetic energy of the block or the block pellet combination once they join together, as shown in figure 3. So let's have a look at figure 3. Just as described there, so we've got the pellet, which is flying into the block, and then that's causing the block to rise by a height of 0.63 meters. Now, if we know the mass of that block pellet combination, we know the gravitational field strength on Earth's surface, we could actually work out the change in gravitational potential energy of this block as it raises over this height. So that's going to come in handy later. Let's just read the rest of it. A pellet of mass 8.80 grams, be careful there, grams not kilograms, strikes a stationary wooden block and is completely embedded in it. The center of mass of the block rises by 0.63 meters, as we just said. The wooden block has a mass of 450 grams. Again, grams, not kilograms. That's going to be important later. Determine the speed of the pellet when it strikes the wooden block. Now, for this question, what I think we need to do is break the question down into steps to get back to the speed of the pellet. So first things first, we're going to need to work out the increase in gravitational potential energy of the block. Now, presumably, according to the conservation of energy, once that block rises, all of its kinetic energy has turned into gravitational potential energy. So at the point of contact with that pellet, all of its energy should be kinetic. So we need to find the GPE, find the kinetic energy of the block, which should be the same as the GPE. So I'm going to write find instead of calculate. Now, once we have that initial kinetic energy, we can use the kinetic energy formula to find the initial speed of the block, which is going to lead us towards the momentum, which we'll look at in a second. Now, a point to note here that actually where I've said block in each of these three cases, I mean the block-pellet combination. Don't forget that, because although the pellet has a very low mass, it could give you an answer that's just about incorrect enough to not fall within the bounds of what's allowable in the final answer. So don't forget to add that 8.8 grams on at the end. The next thing that we need to do is work out the momentum of the block pellet combination, because that's going to be the total momentum after the collision. But obviously the momentum of the block and the pellet. And then once we've got that, we know that due to the conservation of momentum within a collision, that's whether it's elastic or inelastic, which we'll come to later, that should also be the momentum of the pellets before the collision, because remember the block was stationary before the collision, so the only momentum in that situation was whatever the pellet had to begin with. Notice how there I've said find rather than calculate, because it should just be the same as the momentum of the block. The last thing that we need to do is then find the calculate the speed of the pellet from its momentum. There's quite a few steps there. You'll notice it's only a 4-mark question, but what we'll do at the end is we'll break down exactly where those marks are obtained, because there'll be some points, for example, where it says find KE of block. That's not really worthy of 1 mark because it is just the same as what you calculated in the previous step. So first of all then, calculate the increase in GPE of the block. So that gives us 2.84 joules. What you'll notice there is that I put this mass as 0.4588. So I've converted from grams. Remember that the kilogram is the SI base unit, so that's what we need to use as a factor of 1,000 there. Next step, to find the kinetic energy of the block. Well, that's just the same as the change in gravitational potential energy according to the conservation of energy. The next step is to use that kinetic energy equation, half mv squared, to find the speed of the block. Now we will need to rearrange that, but I'll write that here. So that's 3.51 meters per second. Using that speed, or technically that velocity, combined with the mass of the block pellet combination, we can actually find the momentum, just multiply them together. So that's our momentum, which is 1.61 kilogram meters per second, which should also be equal to the momentum of the pellet. And then finally, we just need to divide that momentum by the mass of the pellet to find its speed. So that should give us 183 meters per second, which is fairly fast, but that's what you'd expect a pellet to be. It's always worth checking with these sorts of questions whether your answer is realistic. You know, if you've got 1.83 meters per second, for example, then you'd figure it's probably a power of 10 error somewhere, because that's way too slow for a pellet to cause that kind of impact. So always worth checking whether values are realistic. So in terms of mark allocation, the first mark would be for correctly calculating the gravitational potential energy change of the block. The second mark would be from working out the speed of the block from that energy value. Notice how we've skipped over the kinetic energy step, because that's not really mark worthy. The third mark is for calculating the momentum of the block pellet combination. And then the fourth mark is for working out the final speed of the pellet. The wooden block is replaced by a steel block of the same mass, so that's going to be important. The experiment is repeated with the steel block and an identical pellet. The pellet rebounds after striking the block. Now, by saying it rebounds, that kind of makes me think of some kind of elastic collision. It may not be perfectly elastic though, and that's an important point to make a little bit later on. Discuss how the height the steel block reaches compares with the height of 0.63 meters reached by the wooden block. In your answer, compare the energy and momentum changes that occur in the two experiments. Now, one thing to note here is the use of Newton's second law of motion, which is this. The force is the rate of change of momentum, or you could also write it as is the mass multiplied by the rate of change of velocity, or mass times acceleration. Now, the thing that I'm pointing out here is that actually if the pellet is rebounding, it's traveling in one velocity going forwards, but then it's actually changing velocity by a larger amount. So in the steel block case, this value of delta P is going to be greater because it's actually changing direction and going back the other way. Whereas in the case of the wooden block, the pellet is traveling at some speed and then it's just stopping. So the first thing I would note is that actually where the pellet exerts a larger force on the block is going to move away with a higher speed. So what that would then mean is that the block itself, I'm not saying block pellet combination this time because it is just the block on its own, is going to have a larger speed as it moves away. What that would therefore mean is that if it's got a larger speed, it's got a larger kinetic energy. Remember that kinetic energy is equal to 1/2 times mass times velocity squared. And then the last thing to say is that where that kinetic energy is all converted into gravitational potential energy, the block reaches a larger height. Now, what you might want to bear in mind here is that I've used the abbreviation GPE. It's worth just mentioning to the examiner exactly what you mean by GPE, just so that they know that what you're talking about. Another good thing about this is it can actually save you time. If you write sort of almost like a key, like a legend on the side, it will mean that whenever you use that abbreviation GPE, they'll know what that means each time. So every time you need to use that term, you're saving time on your writing. Just a little trick there. So as you can see, I've included 4 marks in 4 points in black, and those are the 4 marks that you can obtain. It really is just 1 for 1. If you miss any of those, then that's the mark that you miss. And for the final 2 marks, it says discuss which experiment is likely to give a more accurate value for the velocity of the pellets. So thinking about this this metal block, the key here is that whilst it looks as though the collision is elastic, and it certainly is more elastic than the collision with the wooden block, we don't know that it is perfectly elastic. There could still be energy lost in deforming the pellet, deforming the block, production of sound, for example, any kind of friction, any kind of production of thermal energy, for example. So in order for the steel method to work, we would need to ensure that the collision was elastic, and we can't do that. So what we're saying there is that if we knew it was an elastic collision, then all of that GPE that's given to the block, that based on the height that it reaches, will all come from kinetic energy of the block, and presumably that kinetic energy of the block will then also be equal to the kinetic energy of the rebounded pellet that's traveling in the other direction. But that's all an assumption. We can't make that assumption. So the second point to say is what I said earlier about ways in which the energy could be lost through the fact that it's not a perfectly elastic collision. So some examples. So thermal energy loss or heat through deforming the bullet or the block, or just friction. And then also it would make a sound when it collides, quite a loud sound as well. And then just to conclude, because we need to say, obviously at the start it says discuss which experiment is likely to give the more accurate value. We want to say that, well, the least accurate experiment is going to be the steel one, because we don't know where that energy has gone. Now for this question, I think the 2 marks are going to come from the first 2 points, not the third point, because the first 2 points kind of lead into the third point. It's kind of implied. The key information is delivered in saying that, in talking about elastic collisions and talking about energy. To get the first 2 points correct and to get the third point correct is very unlikely. You wouldn't have this level of explanation, this level of detail and reasoning, and then say that the steel block experiment is more accurate. So 2 marks for the first 2 points there. A fiber optic question now, and the first question is asking you to describe the structure of a step index optical fiber, outlining the purpose of the core and the cladding. Now, this is quite a descriptive question. You can see there's a space that's been left just before the text section, so you can draw diagrams here if you want to. What we're going to do is we're going to look at the diagram way of answering the question, and also what we can put into words. So the first thing that you want to say is about the core of the fiber optic cable, and that is going to be the medium for the electromagnetic waves to pass through. Remember that the condition for total internal reflection is that the angle of incidence onto the surface needs to be greater than the critical angle for that particular boundary between those two materials. So in order to maximize that happening, we need to have some cladding around the outside, which has a lower refractive index. Now you'll notice that I'm not abbreviating anything here. I'm not saying EM waves, I'm not saying TIR, making it clear to the examiner that I know what these key terms mean, what they stand for. Now, if we just have a look at a quick diagram. So I'm going to use this to represent my core. What I can then do is draw the light waves passing through. Now, we need to draw the cladding around the outside. I would just use some more straight lines to represent that. Now, you might be wondering, well, why don't we just use air? Why don't we just have the core surrounded by air or even a vacuum? Because that has, the lowest possible refractive index. But actually, we want something that's going to protect the core. Remember, if the core is made of something like glass, it's going to be easily scratched. And if a scratch occurs, it means that light is likely to leave. So that's actually going to be the third point, the third mark that we can write down. Now that's all well and good writing that down as a point in the text, but actually we can show that diagrammatically as well. Now you notice that if the side of that core was flat, then we would just get continued total internal reflection. But where there is this this dent in the glass or a scratch, what you'll notice is that actually the light is hitting the surface at an angle that is lower than the critical angle for that glass air, presumably boundary. So actually we could get some light leave that, and then the intensity or the amplitude of the signal received at the other end is going to be much lower. So we need to make sure that glass is protected. So in terms of your 3 marks, I would say diagrams are fine. If you had diagrams alone, you may not get the entire 3 marks. Even if you were to include plenty of labels, I would say, utilize the text area, but those are your 3 main points. So if you've got a way of illustrating all 3 of those at the same time, then go for it. But I would say stick to those 3 points, write them down to confirm those 3 marks. A signal is to be transmitted along an optical fiber of length 1,200 meters. That's going to come in useful a bit later on. The signal consists of a square pulse of white light, and this is transmitted along the center of the signal consists of a square pulse of white light, and this is transmitted along the center of a fiber. The maximum and minimum wavelengths of the light are shown in table 1. It's going to be the difference in speeds of those colors that's going to cause this thing that we call material pulse broadening, but we'll talk about that very soon. So the first thing to say is actually, in terms of this table, the wavelength values aren't really relevant here. Obviously, they're useful for indicating, where on the electromagnetic spectrum these colors would be, but we're not actually going to use them in any calculations. The refractive index is going to be useful because we're going to use it in an equation relating refractive index to the speed of light in a certain material. So N equals C divided by V. So the refractive index of a given material is equal to the speed of light in a vacuum divided by the speed of light in that material, which means that the refractive index of any material is always going to be above 1. The other one that we're going to use is the speed, distance, time equation. So speed is equal to distance divided by time. You'll notice that where we've got speed in both of those, we can actually tie these two equations together. Now you'll notice that this question is asking you to explain how the difference in refractive index results in a change in the pulse of white light by the time it leaves the fibre. So we're looking at how the difference in refractive index affects the difference in arrival times effectively of those two different colours, because that's what's going to cause that pulse width broadening. Let's write that down first of all, because that's one of the marks that we can obtain. So that's the first mark in that question. Now, just to explain how we can tell this, if we look at the equation that we've just written down, V equals C over N, which is equal to D divided by T. If we were to rearrange that slightly, what you can see there is that actually the time taken is proportional to the refractive index. So the higher the refractive index, the longer it takes for that light to travel from one end to the other of that fibre optic cable. So actually the blue lights will take longer. What it's worth doing for the second mark is writing down our calculations that we can use to find the time difference of arrival between the red and the blue pulses. We can actually see how much this pulse has been broadened. So first of all, for red, 5.84 times 10 to the minus 6 seconds. You'll notice that for the distance I've used that 1,200 meters that was given in the question. And then 5.87 times 10 to the minus 6 seconds for blue. Last thing to do is to work out that time difference between those two pulses. So we end up with about 3 times 10 to the power of minus 8 seconds for the time difference, and that's where we would obtain that second mark. Just as a side note, you'll want to refer to this as material pulse broadening rather than pulse width broadening. That's what the mark scheme wants from you. It's better to be using the exact correct terminology so there's no uncertainty with the examiner. So for the last part of this question, it's asking you to discuss two changes that could be made to reduce the effect described in part 5.2 or the previous part of the question. So this material pulse broadening that we mentioned previously. Now, the first thing that we can do is use a monochromatic source of light, and what that will do is if every ray of light travels has the same wavelength, then every ray of light will travel at the same speed and therefore reach the other end at the same time. The second thing that you could say is you could use shorter repeaters. So the repeater, I guess, machines that go between the strands of glass, between the cores, what they do is they strengthen the signal if it's traveling over long distances. As you can see from the last part of the question, that fiber was 1,200 meters long. That signal is going to diminish as it travels over a certain distance. No material is perfect, so we use these repeaters to actually boost the signal. But if we make those closer together, we can actually use each one to reform the signal and have that happen more often, so that this material pulse broadening can't happen as much over a larger distance. And then the last thing that you might want to do is use something called a monomode fiber. Now, a monomode fiber is just a thinner strand for the core. It means that there's less variation in the possible paths that the light beam can take, and therefore all rays of light will travel approximately the same distance and therefore will arrive at approximately the same time. And then that pulse broadening generally is lessened. Now for this question, It's very difficult to say where exactly the marks come from. You'll notice that I've put 3 points in, and it's only a 2-mark question. I think I would advise playing it safe on this one. Include all 3. Give a varied argument with plenty of different examples. That way you can't go wrong. I don't think it's as simple as 1 mark per point. I think you really do need all 3 to get those 2 marks. It's important with this question, of course, that you understand the difference between modal broadening and material broadening. So modal being this idea with monomode fibers, a broadening that's caused by a difference in path due to a wider fiber, and material broadening actually to do with the colours of the light travelling at different speeds and therefore arriving at different times. So we now have what feels like a reading comprehension question, all to do with sort of waves and sound. As you can see, it's entitled Measuring the Speed of Sound in Air. So if we first of all just read through the passage and identify any bits of information which might be useful later. So read through the following passage and answer the questions that follow it. After the wave nature of sound has been identified, many attempts were made to measure its speed in air. The earliest known attempt was made by the French scientist Gassendi in the 17th century. The procedure involved timing the interval between seeing the flash of a gun and hearing the bang from some distance away. So you can see there, actually seeing the flash and hearing the bang. We're going to be looking at light versus sound. That's going to come in useful later on. Gassendi assumed that compared with the speed of sound, the speed of light is infinite. The value he obtained for the speed of sound was 480 meters per second. There's a reference value there, it might be used in some kind of calculation. He also realized that the speed of sound does not depend on frequency. A much better value of 350 meters per second was obtained by the Italian physicists Borelli and Viviani using the same procedure. In 1740, another Italian, Bianconi, showed that sound travels faster when the temperature of the air is greater. In 1738, a value of 332 meters per second was obtained by scientists in Paris. This is remarkably close to the currently accepted value, considering the measuring equipment available to scientists at that time. Since 1986, the accepted value has been 331.29 meters per second at 0 degrees Celsius. Now, what you'll notice is that as you progress through that text, the values for the speed of sound get closer and closer to what we class as the true value, which is the one at the bottom there. So you can see it goes from 480 to 350, 350 to 332, and then 332 to 331.29. Not only is that final value considered to be the most accurate, it's also the most precise because it's to 2 decimal places. So for the first question, suggest an experiment that will demonstrate the wave nature of sound, line 1. So line 1 just says, after the wave nature of sound has been identified, many attempts were made to measure its speed in air. So actually the text in this question isn't particularly helpful. You need to know about the general properties of waves, because obviously sound is a wave, and therefore how we can demonstrate one of those properties. So let's write down some examples of properties of waves and see how we can apply that to sound. Now, when we look at this, 2 of these examples of wave behavior are trickier to observe, trickier to show experimentally, but one's actually quite straightforward. So refraction, you could do, obviously it requires a wave to pass through a boundary between 2 different materials. You need some quite sophisticated apparatus to show that sound can be refracted between materials, and also diffraction, coincidentally, would actually mean that this method is trickier because diffraction is happening at the same time as refraction, and it will cause all kinds of changes in direction. So we're not going to use refraction for this one. Reflection, you could show that sound is reflected quite easily. You could look at sort of echoes, for example, if you were to go into a cave. The tricky thing about this one is that actually, if sound were to behave as a particle, it could also reflect. So it's very difficult to distinguish the wave and particle nature just using that method. So we're not going to use reflection. We are actually going to use diffraction, which, as you know, involves the sound or any wave passing through a gap or around an obstacle, and if it changes direction under those conditions, then it has been diffracted. So let's write that down. So a fairly tangible example there, use a doorway, use some kind of speaker, put a microphone around the corner. If that microphone doesn't detect anything around the corner, then the wave hasn't spread out, it hasn't diffracted, but yeah, vice versa. If it does, then it has. So yeah, and then there's your 1 mark. So the next part, using Gassendi's value for the speed of sound from line 6, we'll look at that in a second. Calculate the time between seeing the flash of a gun and hearing its bang over a distance of 2.5 kilometers. So just looking at line 6, we can see there that the value he obtained for the speed of sound was 480 meters per second. So this is a very straightforward question. We've got a speed of sound and we've got a distance. We just need to know the time difference. So speed equals distance divided by time. Let's write that down first of all. And we want to rearrange that to make time the subject, because that's what we're trying to work out. So time is equal to distance divided by speed, or distance divided by velocity, or technically displacement divided by velocity if we're working in vector quantities. So let's input our values. So don't forget to put times 10 to the power of 3. Remember, this is 2.5 kilometers. That's an example of where you could slip up, and where this is a 1 mark question, you either get the mark or you don't. If you'd use 2.5 meters, for example, you would unfortunately miss that mark. So the answer there should be 5.2 seconds. Now, there's no need to round that value any further because the values that were given are already to 2 significant figures, and our answer is to 2 significant figures. So we need to keep that consistent. Explain why it was necessary to assume that compared with the speed of sound, the speed of light is infinite, line 5. So let's take a look at line 5. So Gassendi assumed that compared with the speed of sound, the speed of light is infinite. So actually, it's just quoting that that part of the text. Now, so what you'll notice here is actually what you're timing is the time between the difference in time between that taken by light and that taken by sound. So the lights and the sound are emitted at the same time. They both reach the observer, but we want that time difference to be just the time taken for the sound. So we would need to assume that the speed of light is infinite, i.e. it doesn't take any time to reach the observer, because if something travels at infinite speed, then for any distance, it will travel there in 0 time, which is technically impossible, but by comparison to the speed of light, we can treat it as infinite. And just to add an extra bit of clarification there in terms of why that is. So like I said there, we're actually measuring the time difference between the lights arriving and the sound arriving. But if the light gets there in 0 seconds, then that time difference will be just the same as the time taken by sound, which is what we want in the first place in order to make those calculations. So explain one observation that could have led Gassendi to conclude that the speed of sound does not depend on frequency. So that's line 7. Let's just take a look at line 7. So he also realized that the speed of sound does not depend on frequency. Okay, so it's quoting that again. Now, what we need to bear in mind here is that the sound produced by something like gunfire, like an explosion, is quite a natural sound in the sense that it's not orchestrated by frequency in any way. It's not manufactured, it's not artificial. It has a range of frequencies. Now, if the speed of sound did depend on frequency, then all of those frequencies of sound produced by the gun, they would all reach the observer at different times. Now, since we know that they will arrive at the same time, there's no sort of prolonged sound produced by the gun that increases or decreases in frequency, if you can picture that, then that must mean that all frequencies arrive at the same time and therefore travel at the same speed. Therefore, the speed of sound is not dependent on frequency. So let's put that into words. So 2 marks there, 2 points made. Nice and straightforward. Explain how the value obtained by Borelli and Viviani was much better than that obtained by Gassendi, line 8. So it mentions there a much better value of 350 meters per second, and that's compared to the 480 that was previously obtained. So let's go back to the question. Now, we know that the speed of sound, as it's given later on in the question, is 331.29 meters per second. You could call that the accepted value. Now, 350, as you can probably see, is a lot closer to 331.29 than 480 is. So calling it much better, that's not really the most scientific way of putting it, but what we mean by that is it's closer to the accepted value. You could say that it's more accurate, for example. So there's your 1 mark for pointing out that it's closer to the accepted value. So this question wants us to use this, I say complicated looking equation. It's really one that we just need to put the numbers into and get a number out. Now the passage actually does give us an example value of C and its corresponding value of theta. So by inputting this value and this value, we can obtain this value of K. So let's look back at the passage of text. So what you can see here from the very last line is that the value of C can be given as 331.29 meters per second, and that's at 0 degrees Celsius. So what we can do is put those numbers straight into the equation and find a value of K. Nice, easy 2 marks there. Now it's really important here that we observe the units that this question wants. It is as easy as it looks in this case because we have a value in degrees Celsius and it wants the temperature in degrees Celsius to put into the equation. But sometimes you have to be careful because it might give you a value in Kelvin, or the equation might ask for a value in Kelvin, and you need to make that conversion. This time we don't need to, however, so we're just going to put those numbers in as they are. So you can put the numbers in to this equation and then rearrange. What I'm going to do is I'm going to rearrange first and then make the calculation in one go to get a nice value out. So K is equal to C divided by the square root of theta plus 273.15. Let's put those values in. So that gives us a value of 20.045. Now, we don't need to worry about units because those are actually given to us in the answer space there. You may wish to round the value down, but I would say you could probably leave this one because the values that were given, the 331.29 and the 273.15, are actually to 5 significant figures. So it's perfectly fine to put your final answer to 5 significant figures. It's always worth double checking that it's okay to put the value in degrees Celsius rather than Kelvin. State the steps taken by the scientific community for the value of a quantity to be accepted according to line 13. So let's look back at the text at what line 13 is saying exactly. This is remarkably close to the currently accepted value considering the measuring equipment available to the scientists at that time. Since 1986, the accepted value has been those values that we've dealt with before. So let's go back to our question. So the key with this sort of question is to think about how we can validify an experimental value. Now, typically, the best thing to do is compare it to what other people have. Now we can sort of science that up a little bit by saying we can publish our method and our value and make it clear how we've obtained that value so that others can then repeat that experiment. What others can then do is publish their values for the same method. If they obtain the same value or a similar value, then that makes your value seem more reliable. If they obtain a completely different value, then it's clear that something's gone wrong and actually your method could be incorrect. So the first point to make, the method and the value are published. And then the second thing that you want to say is that others can then carry out that exact same method to see if they obtain the same value. So 2-mark question there, 2 points made. It really is 1 for 1. If you miss one of those, you miss a mark, 2 marks. A multiple choice question now, and one that's probably requires you to put more than 1 mark of work in, but actually because it's multiple choice, you only get the 1 mark out for just getting that correct answer, so it's kind of all or nothing. But if we take a look at this, at how this question is worked out, and you'll see that if it were any other kind of question, you'd be awarded a much larger number of marks. So we've got the nucleus of, I believe, beryllium, 9 nucleons, 4 of which are protons. It captures a proton and emits an alpha particle. So the first thing we want to do is identify what these particles are, especially that alpha particle, and try and work those into some kind of equation. Now we know that an alpha particle is a helium nucleus with 4 nucleons, 2 of which are protons. And a proton is just a proton. It has a nucleon number of 1, and it has or is 1 proton. You'll see that that comes in useful when we write out our equation to try and work out what the numbers should be on our product nucleus. So you can see that I've written out the equation with everything except that product nucleus. The question has told us the story, and we've put that into equation form. Now, what we need to do is balance the numbers on both sides. So you can see that the total nucleon number should be, well, it should add to 10. And you can see on this side, we've only got 4 so far. So in order to get 10 on the right-hand side, this number would need to be 6. Now we can do the same for the proton number on the bottom. So 4 plus 1, there should be 5 on the left-hand side. That means there needs to be 5 on the right-hand side. We've got 2 so far. So 5 minus 2, that's going to be 3. Now, if we look at our options here, the only one that's going to have a 6 and a 3 is lithium. So the answer is C. Another multiple choice question now, and this one is rather qualitative. We've got a series of points about X-rays in comparison with UV radiation, and we essentially just have to identify the one that's correct. The way I would tackle this question is by trying to figure out in my own mind why the other 3 are incorrect, and therefore deducing the correct answer. So if we just start with A and work our way down, the first one, X-rays have a lower frequency. Well, we know that that's incorrect because as you move from radio all the way up towards gamma, you increase in frequency, and X-rays, they just have a higher frequency than UV radiation. But that's just a case of knowing the order of the sections of the electromagnetic spectrum. So it's not going to be A. X-rays travel faster in a vacuum. Well, we know that's not true because all electromagnetic waves travel at 3 times 10 to the power of 8 meters per second in a vacuum, and that doesn't vary with type of radiation, frequency or wavelength, so it's not B. For option C, X-rays do not show diffraction and interference effects. Well, X-rays are types of waves. Diffraction and interference effects are their properties of waves, so that would also be incorrect. Now, by deduction, we found that D must be correct. Using the same element, photoelectrons emitted using X-rays have the greater maximum kinetic energy. Well, we can actually use Einstein's photoelectric effect equation to answer this, to confirm that it is correct. What we can see from this equation is that the Planck constant multiplied by the frequency of the certain type of radiation is equal to the maximum kinetic energy of the emitted photoelectrons. So that's this here, plus the work function of the material. Now, we're using the same element here, so that work function is going to remain the same. So what we're saying there is that we need to find a relationship between frequency and maximum kinetic energy. Now, as we found when looking at option A, X-rays actually have a higher frequency. So what we should find from this equation, and there's actually a proportionality here, is that the higher the frequency of the electromagnetic wave, the higher the maximum kinetic energy of the emitted photoelectrons. So actually, photoelectrons emitted using the X-rays will have the greater maximum kinetic energy. So actually, D is correct. Monochromatic radiation from a source of light, source A, is shone onto a metallic surface and electrons are emitted from the surface. When a second source, source B, is used, no electrons are emitted from the metallic surface. Which property of the radiation from source A must be greater than that from source B? Now, the thing to notice first of all here is that we're using the same surface in both cases, which means that the work function is going to remain the same. So that's this value of phi. Now, the difference here is that one type of radiation allows electrons to be emitted and one doesn't, which tells us that photons from source A are going to have more energy than photons from source B. So the energy of a photon is dependent on its frequency due to this equation. And if we use Einstein's photoelectric equation as well, we can see a relation there that ties in the work function also. So what's actually happening here is where source A has a higher energy per photon, it also has a higher frequency. Now, just to go through why it's not the other answers, it can't be wavelength because frequency is inversely proportional to wavelength. So answer D is incorrect. And in terms of amplitude and intensity, well, there's an equation that relates both of those together. So if we can prove that one of them is wrong, we can actually prove the other is wrong. So if I just write that down first of all. Intensity is proportional to amplitude squared. Now, intensity is all about the number of photons per unit area per second. Obviously, there's an energy tie in there in terms of the number of joules, but the higher the intensity of a source of radiation, the more photons we're dealing with. So actually, that doesn't affect whether photoelectrons are emitted or not. So where intensity has to be wrong, amplitude must also be wrong. In this multiple choice question, we've got two wires, wire X and wire Y, which are joined end to end and used to support a weight W. We're given four options here, all involving stress, strain, tension, elastic energy, all kind of materials related terms. It means that we're going to need to use the Young modulus equation. Now, the key detail to pick out before we go any further is that they're both made of copper. That will then therefore mean that they'll both have the same Young modulus. Now, if we think about what exactly is happening to this combination of wires in terms of Newton's third law, what we can see is that the tension, in theory, should be the same in each wire. If you picture, instead of having two wires, perhaps a human ladder, a load of people in a line supporting each other, perhaps from a helicopter or something like that, if you can picture it, and each person is supporting the next person down. If I just draw that as a simplified diagram. So you can see there, you've got several particles which are all supporting each other. Now, for this kind of question, I think you need to make the assumption that anything that's supporting the weight is going to be itself weightless. So the wires don't have any mass, therefore there's no weight contribution to the forces. Now, if you picture this kind of human ladder, the person at the top is going to need to be the strongest because they're going to need to support all the people below them. And the lower down you are in that ladder, the less you'll need to support. Obviously, that is different because of this kind of weights contribution. If all of those people were weightless, technically, the only force that each person would be holding is that weight right at the bottom. So if we draw some arrows to represent the forces acting on each of those people, so the person at the bottom, you've got a tension that's pulling it down, and you've actually got the same tension that's pulling it up. Now, for that weight at the bottom, you've got a tension acting upwards, but there's a weight force pulling it down. And you can see this continues all the way up. Now, if weight of the individual particles were a thing, you'd have to add in extra arrows and the whole thing would become unbalanced. So we're actually going to treat each of those people as weightless. So as you can see there, the tension force in wire X and wire Y should be the same. Now, just a quick clarification on why it's not the other three answers. If we look at the equations involved, so what I've done there is I've written the Young modulus equation in terms of force, original length, cross-sectional area, and extension. That's a combination of the stress and strain equations as well. So stress being equal to force divided by cross-sectional area, and strain being equal to extension divided by original length. So just looking at those other options. So the strain in X is the same as that in Y for option A. Well, if we look at what's actually happening in the diagram, the Young modulus is equal to stress divided by strain. So if both materials have the same Young modulus and the forces on each are the same, what we can actually see is that technically they will have different stresses because their cross-sectional areas are different. So where wire Y has a larger cross-sectional area, technically its stress should be smaller. Now, if its stress is smaller, that will therefore mean that its strain is also smaller. So what we're seeing there is that the strain in Y is smaller than the strain in X. So actually, they're not equal. So therefore, it's not option A. For option B, the stress in Y is greater than that in X. Well, we just pointed out that actually, because wire Y has a larger cross-sectional area, if the forces are the same, because they're both just the tension force, then that would mean that it's the other way around. The stress in X should be greater than the stress in Y. So that's incorrect. Now for this last one, the elastic energy stored in X is less than that stored in Y. If we just write down the elastic potential energy equation. So it's probably best not to get the spring constant K involved too much. We don't want to overcomplicate things, but effectively the elastic potential energy stored is equal to 1/2 times the force of extension multiplied by the extension itself. Now, if the forces are both the same, what we can say is that actually where wire X has a larger strain, we would assume that it's got more extension. If it's got more extension, then there will be more elastic potential energy stored within it because it's proportional to the elastic potential energy. So actually, the elastic energy stored in X should be greater than the elastic energy stored in Y, so D is incorrect. For this multiple choice question, we're interested in two equations, one for kinetic energy and the other for de Broglie wavelength. So let's write those down first of all. Now, what I'd recommend for this is if we first of all find out what effects kinetic energy has on the speed of the electron, and then therefore use that change in speed of the electron to find out what the change in de Broglie wavelength is, because you can see that the speed is what these two equations have in common as a variable. Remember, the mass of the electron stays the same. So the first thing we need to do is find out by what factor the speed of the electron changes. So the initial speed is equal to the square root of 2 times the initial kinetic energy divided by the mass. So all I've done there is I've rearranged the equation to make the speed of the electron the subject and just put I to represent initial, because we're going to look at the final kinetic energy and the final speed. So the final kinetic energy after the change is 4 times what it was originally. So making a substitution, so we can see we put a factor of 4 in there, but because it's inside the square root, we can take that 4 out and just multiply the entire square root by 2 instead of putting a 4 on the inside. Remember, the square root of 4, sorry, is 2. So making a substitution again, remember that the square root of 2 times the initial kinetic energy divided by the mass, which I can see up here, is also equal to VI. So we can literally just say 2 times the initial speed. So algebraically, what we've said there is that the speed after the change is equal to double the speed before the change. So the speed doubles. Now, we don't need to do this lengthy process for the second equation. We can see quite clearly there that the de Broglie wavelength is inversely proportional to the speed. So if the speed doubles, that must mean that the de Broglie wavelength halves. And the only answer where the de Broglie wavelength halves is answer B. So there's our answer. For this multiple choice question, you just need to know what the pulses would look like after they've passed by each other. There's not really any particular way of getting towards the answer by knowing other things. You just kind of need to know how they behave during this superposition process, if you like. So let's just look at the options for this question. The first option is what you would observe as the two pulses are passing over each other. So that option would occur, but we're interested in when they've already passed through each other. So actually A would not be correct. Now we're going to come back to B, because interestingly B is the same shape as it is before they pass through each other, but we'll return to that one. As you can see for question C, they pass through each other. It's as if they've not interacted at all. So you can see that the top one is traveling this way and the bottom one is traveling this way. Now that's actually what happens when two waves on a piece of string, or two pulses on a piece of string, pass through each other. Afterwards, it's as if they never interacted. They just carry on in the same direction in the same way. But we're going to talk about B and D anyway. Now for part B, as you can see, that would only work if the upper pulse were to switch from top to bottom as it was passing through the lower pulse, and that just doesn't happen. Again, like I said, they pass through each other and it's as if they never interacted. They just carry on as they were. And I think for part D, it's suggesting that the pulse is spread out, they become more broad. Well, there's no evidence of that happening. That's just not a thing that's known to happen, so that's also wrong. So B and D are incorrect. So once you understand what's going on with monochromatic light as it passes across a boundary for this multiple choice question, this question becomes very straightforward. So let's just draw a quick diagram of a light wave with its wavefronts passing across a boundary. So I've drawn the two regions there, air and glass, and you can see that the wavelength actually gets shorter. Now, we can tie all of this together using the wave speed equation. So V equals F lambda, wave speed equals frequency times wavelength. What actually happens as the wave approaches the boundary is that the wavefronts, obviously they hit the boundary, the surface, at a certain rate, a certain number per second. And that means that they're actually released from that boundary into the glass at that same rate. So technically the frequency is conserved across that boundary. So in both air and glass, the frequency remains the same. We do know, however, that due to the difference in refractive index between air and glass, the light actually travels slower in the glass than it does in the air. What that then means is if we keep the frequency constant in this equation and we make the speed lower, that means that the wavelength is also going to decrease. So the two quantities that change are speed and wavelength only, so the answer has to be B. So for this multiple choice question, you're required to know what effects the intensity of radiation has on the photoelectrons that are emitted. What we'll do is we'll just go through each one, each option, and identify why the three incorrect ones are incorrect and why the correct one is correct. So starting with option A, the work function. Well, the light is instant on the metal surface of a photocell. That metal itself doesn't change, so the work function doesn't change. Remember, the work function is specific to the type of metal being used, so that's incorrect. For part B, the minimum frequency at which electrons are emitted, well, actually the threshold frequency is specific to the metal as well, and that is that minimum frequency is actually proportional to the work function. It can be shown through this equation. So phi being the work function, h being the Planck constant, and f0 being the threshold frequency. So B is also incorrect. Now C is correct, and the reason for that is the current through the photocell is it relates to the rate of flow of charge. Now that current is proportional to the rate of flow of electrons through the circuit. Now that rate of flow of electrons is governed by how many electrons are emitted from that metal surface per unit time. And that is affected by the intensity. Remember, the intensity affects the rate of emission of photoelectrons, therefore the rate of flow of charge, whereas the wavelength and the frequency will affect the kinetic energy of those electrons if they are released. But we'll get to that in a second. So the reason why D is incorrect is because the speed of the electrons obviously relates to their kinetic energy, and the kinetic energy of those photoelectrons, should they be released, is all determined by the frequency of the incident radiation. We're not changing the frequency, we're changing the intensity. Remember, the frequency of the radiation relates directly to the energy of the incoming photons, so D is also incorrect. Multiple choice question on electricity now, and you can see we've got this potential divider circuit where we've got a variable resistor in one section and then just a fixed resistor in the other, and we're interested in what happens to the voltmeter and ammeter readings when the resistor marked R changes its value of resistance. So here are the four options. Got increases and decreases, and one unchanged in the case of option D. What we'll do is we'll just look at the ammeter reading first of all, see if we can cancel off some of these options, and then look at the voltmeter reading to refine our choice further. So when the resistance of R is decreased, what we'll observe is that the overall resistance of this circuit should actually decrease also. Now remember, the resistance of the circuit is the ability of the circuit to restrict current. So if the resistance is going down, then the current must increase. So the ammeter reading is going to increase. What we can see from this table then is that it can't be C or D because they don't have an ammeter reading increase. So we're left with A or B, the voltmeter reading either increasing or decreasing. Let's have a look again. Now what we can say here is that if the resistance of the variable resistor is decreasing, then that means it's going to be taking less energy from the circuit, which means the potential difference across that resistor is decreasing. Now, what you'll notice here is that the voltmeter and the variable resistor form a closed loop. And what Kirchhoff's second law tells us is that within a closed loop, the sum of the EMFs is equal to the sum of the potential differences. So actually what's happening there is that the potential difference across the voltmeter is the same as the potential difference across the variable resistor. So if the PD across the variable resistor is going down because its resistance is decreasing, then that would mean that the reading on the voltmeter would also have to decrease. So our answer would actually be B. In the circuit shown, V is a voltmeter with a very high resistance. The internal resistance of the cell R is equal to the external resistance in the circuit. Which of the following is not equal to the EMF of the cell? Then we've got 4 options there. Now, for this question, I think the best thing to do is to just go through each answer and just assess whether it's plausible, whether it's right, whether it's wrong, and see if we can narrow down to a correct answer. So the first option here, the reading of the voltmeter when the switch S is open. So what we're saying there is when the switch is open, is the reading on the voltmeter equal to the EMF of the cell? So what you'll notice with this part is that actually there is no current flowing through the main part of the circuit, which means that there's no potential difference across the resistor. The PD across the internal resistance is 0, so this one up here. Now what that then means is within this closed loop, just up here, there are only 2 significant voltages, and that's the voltmeter and the EMF of the cell. So actually those would have to be equal according to Kirchhoff's second law. So where that EMF would be equal to the reading on the voltmeter when the switch is open, A would not be correct. So for B, the chemical energy changed to electrical energy when unit charge passes through the cell. So actually, it's almost like that answer is trying to confuse you. Basically, EMF is energy transferred from chemical energy per unit charge into electrical energy. So it's really just giving us the definition of EMF, and where the EMF of the cell is the chemical energy transferred to electrical energy per unit charge, B would be incorrect as well, because it's not that. For C, twice the reading of the voltmeter when the switch S is closed. Now I would say this is the most complex one. You really need to think about how Kirchhoff's second law might apply, for example, and how the voltages line up. So looking at this diagram, you can see that the voltmeter is connected in such a way that we may as well put it directly across the external resistance, because these 2 connection terminals could just be connected across the resistor, and it would give exactly the same value. So what we're interested in is in this closed loop, the outer closed loop this time, because we're saying that switch S is closed, the EMF of the cell has to be equal to the sum of the PDs. Remember Kirchhoff's second law. So actually each of those resistors, where they are identical resistances, each of those resistors has half of the number of volts of the EMF. So if we look at this voltmeter in more detail, we can see that the PD across it should be equal to the PD across the external resistance. And and the PD across that external resistance should, in theory, be a half of what the EMF is, because there are two of those resistances in the whole closed loop. So, for example, if the EMF provided by the cell was 2 volts, then that would mean that each of the resistors would have to be 1 volt. And when you look at the PD across the external resistance, it would be 1 where the EMF is 2. If the EMF was 4 volts, each of the resistors would have to be 2 volts. So there's that half or double relationship there. So actually, where the EMF is double the reading of the voltmeter, C is not correct. So we actually narrowed down here that D is correct. So let's just fill that in. But let's look at this in more detail anyway. The electrical energy produced when units current passes through the cell. Well, let's go back to what we talked about with option B and how we're looking at the definition of EMF. There is no quantity that involves energy per unit current. So actually, it's quite a minor detail, but it makes answer D incorrect. So that's why the answer is D. The electrical energy per unit current, whatever that is not equal to the EMF. So D is the correct answer for this question. So diffraction gratings for this multiple choice question. There's a few different statements that are made. Obviously, only one of them is obviously correct, but actually 3 of them use the same equation, and we can work the answers to those out fairly quickly. So if we start off by writing down the diffraction grating equation, so there we have n lambda equals d sine theta. So the number order that we're dealing with multiplied by the wavelength of the light is equal to the spacing of the gaps in the grating multiplied by the sine of the angle of the individual maximum that we're looking at. Now, an important point to make here is that actually we're given the number of lines per meter, not the number of meters per line. So what we actually have to do is find the inverse of this 6 times 10 to the power of 5, because that's going to be the value that we need to put in. What we can do instead is actually adapt our equation to include this. So what I've written there is 1 over capital N sine theta, and by capital N I just mean this number of lines per meter. So we're interested in the angle of these orders, so we're going to rearrange this equation to make the angle the subject. So what we do now is just input the values that we're given. We've got a wavelength. Bear in mind that we need to convert that into meters from nanometers. We've got the number of lines per meter, and then we're just looking at the different orders, which are the different values of lowercase n. So what we can see there is that actually by using the values that we've got, the first order is found to be 17.09 degrees, which is approximately 17 degrees. So actually, we've proven already that answer A is correct. But let's go through anyway and just confirm that the other ones are incorrect. So the second order, let's just change the numbers around. So we'll change this 1 here to be a 2 and see what angle that gives us. So that actually gives us 36 degrees, so answer B can't be correct. So let's find out if the third and higher orders are produced. So let's change the numbers to 3. So that actually gives us an angle of 62 degrees. Now the condition on which a third order wouldn't be produced would be if that angle were to come out as being higher than 90 degrees, because that's not actually possible from a diffraction grating, because that actually means that the light is bending round past the plane of the diffraction grating, which it just wouldn't be possible. So we know then that the third is produced, so C can't be correct, even if those higher ones can't be produced. And then finally, a grating with more lines per meter could produce more orders. Well, we can actually just look at the original equation for this. If we look at this version of the equation, so we've got theta equals sine to the minus 1 of n lowercase n lambda. If we have more lines per meter and capital N was larger, that would increase the value of sine to the minus 1, which would mean that theta would be higher for any given value of lowercase n for any given order. So what that would actually mean is that all of the maxima would spread out to larger angles, and therefore the outer maxima, for example, the third one, will eventually be pushed off the edge of that 90-degree boundary. So actually having more lines per meter will mean you have fewer orders, not more. So for this multiple choice question, you just need to know what happens during the ionization process. There are some answers which are trickier to narrow down, but there are some which are obvious. For example, one that doesn't obey the conservation of charge. So if you look at option D, that one's clearly incorrect, because whilst it's correct that the electron has taken away an electron from the neutral atom, there needs to be a loss of negative charge from that atom itself, so it needs to become positive. So that should hopefully give you a clue as to what the correct answer is, but actually from that we can see that answer D is not correct. Now, answer A we know is not correct, because an excited atom clearly hasn't been ionized. There's no mention of it being ionized. For it to be excited, we need to have the nucleus become more energetic. So A is incorrect. Now, during the ionization process in this form, when the electron comes in, it knocks into an electron in one of the shells of the atom, and it removes that electron. So the only one that is correct is going to be C. You could argue that it's B, in that electron could just be absorbed by that atom, and then that atom just has that excess electron. But that's not what happens during this particular type of ionization. So the electron comes in, collides with another electron, two electrons move away, leaving a positive ion behind. So the answer is C. This multiple choice question, you're given two forces of 6 newtons and 10 newtons, and they act on the same point. So we want to know which of the following could not be the magnitude of the result. Now, what I would do for this one is draw a free body force diagram, but actually that free body force diagram is going to change. This question hinges on the direction of those two forces. Now, those two forces could act in the same direction, so I'll just quickly draw that. So that would mean that the resultant could be 16 newtons. So that would mean that A is not correct. Now let's have a look at if these forces were in opposite directions. Now that would mean that the resultant is 4 newtons. This is actually the smallest magnitude of resultant force that we can obtain. Those forces are fully opposed to each other. There's no more that 6 newtons can take away from that 10 newtons. So actually what we've shown there is that 3 newtons is not possible, it's too small. Now you might be wondering, well, how do we get 8 newtons or 5 newtons? Well, we could have these forces act at different angles. Instead of being in opposite directions or in the same directions, you could have them at an angle, and you could form some kind of triangle, a right angle triangle, for example, and the values that the resultant force will take will therefore be anywhere between 4 and 16 newtons. And obviously 8 and 5 are both between 4 and 16, so B and C are not correct. A car wheel nut can be loosened by applying a force of 200 newtons on the end of a bar of length 0.8 meters as in X. So that's the diagram on the left. A car mechanic is capable of applying forces of 500 newtons simultaneously in opposite directions on the ends of a wheel wrench as in Y. And then you've got the two diagrams there, one where the force is being applied on one side of the nut, the pivot, and the other where there are two forces, one on each side, and they're acting in opposite directions. what it's asking is for you to work out what the minimum length L of the wrench needs to be for you to loosen this wheel nut. What you'll notice in scenario X is that if you have a force of 200 newtons, then you can apply that at a perpendicular distance of 0.8 meters, and that will give you a sufficient moment. So the first thing I would do is work out exactly what that moment needs to be in Newton meters. So moment is force multiplied by perpendicular distance. So the moment required is 160 Newton meters, and that needs to be provided by those two 500 Newton forces. Now, because there's two of those forces in scenario Y, we can actually split the moment required between the two of them. So each force would only need to provide 80 Newton meters of moment. So what we ought to do is work out how far away from the pivots those forces need to be applied in order to be 500 Newtons. So each of those forces need to be 0.16 meters away from the pivot. Now, if you look at the possible answers for this multiple choice question, you'll see that 0.16 is one of those answers. Now, this is where the question could catch quite a few people out. You might see your answer and think, oh, well, that must be the answer because it's one of the options on the list. But actually, what the question is asking for is what the minimum length L of the wrench needs to be. And that is this length here. It's the distance between the points of application of both forces on that wheel wrench. So actually that distance is double the distance of one of the forces from the pivot. So it's double 0.16. So actually the answer is 0.32 meters. So be very, very careful there. A ball bearing X of mass 2m is projected vertically upwards with speed u. A ball bearing Y of mass m is projected at 30 degrees to the horizontal with speed 2u at the same time. Air resistance is negligible. Which of the following statements is correct? Now, the interesting thing about this question is that actually the mass of the ball bearing shouldn't matter, because when you project any object up into the air, as shown in the question, it's subject to the same laws. It's subject to the same rate of acceleration due to gravity. You would use the same Subat equations, for example, the same equations of motion. What we're interested in is actually this u and 2u for the two ball bearings. Now, if we're projecting something at 30 degrees to the horizontal, let's just first draw a diagram for that. Now, what you'll notice is the vertical component, which is what we're interested in, because that's the bit that's subject to gravity, is going to be quite familiar. So sine of 30 is equal to O divided by H, or opposite divided by hypotenuse. And in this case, it's the vertical velocity divided by 2u. So let's just write that down. Now, if we rearrange that to make v the subject, what we should find is that actually sine of 30 is 0.5. So it cancels with the 2 at the start of that expression. And then that just leaves us with u. So in actual fact, both ball bearings have the same vertical velocity upwards of just u. So on that basis, they'll both reach the ground at the same time. So the correct answer is C. What is the relationship between the distance y travelled by an object falling freely from rest and the time x the object has been falling? And then we've got 4 proportionalities there. Now, the equation that I would refer to is the easiest one that combines time and distance travelled, and that is going to be s equals ut plus half at squared. Now, you'll notice that the initial speed of an object in this case is going to be 0 because it's falling freely from rest. So we can actually simplify this equation down because u is equal to 0. What we can see there then is actually the distance is proportional to time squared because s is proportional to t squared. Y is going to be proportional to x squared, so the answer is A. A car exerts a driving force of 500 newtons when travelling at a constant speed of 72 kilometers per hour on a level track. What is the work done in 5 minutes? Now, the first thing that I would do with this question is convert that 5 minutes into seconds because we want to work in SI units. So that's 300 seconds. Now we've got a force of 500 newtons and we're going at a speed of 72 kilometers per hour. So we also want to convert that 72 kilometers per hour into meters per second. So let's do that as well. So that gives us 20 meters per second. You'll notice that I've converted it into meters per hour first by multiplying it by 1,000 and then converting it to meters per second. Now, we need to work out which equations we can use to get to this energy value. So the first thing I would say is work done, which is the energy value, is equal to force times distance. But the other thing to say is that distance is equal to speed multiplied by time. So if we combine these equations together, what we can say is that actually the work done is equal to the force times the speed times the time. So if we multiply all of those values together, we should end up with 3 million joules, which is 3 times 10 to the 6, which should be answer A. Two masses hang at rest from a spring, as shown in the diagram. The string separating the masses is burned through. Which of the following gives the accelerations of the two masses as the string breaks? Acceleration of free fall is g. And then we've got 4 possible answers here, all involving different multiples of that value of g for acceleration of the 1 kilogram mass and acceleration of the 2 kilogram mass. The first thing to say about this question is that after the string breaks, the 2 kilogram mass is going to be in free fall. There won't be any other forces acting on that mass other than its own weight, so it will just accelerate downwards at 1g. And from that, we can deduce that answer B is incorrect. So the answer needs to be either A, C, or D. Now, if we look at the forces acting before and after with this diagram, initially, the mass or the bottom of the spring is going to be in equilibrium because it's at rest. The downward force, or the weight of the two masses, is going to be 3g newtons. Bearing in mind that W is equal to mg, or weight equals mass times gravitational field strength, which is also just g. This will mean that the upward force provided by the spring is going to be 3g newtons as well. Now, after the string is burned, the 2 kilogram mass is disconnected, so the only weight, the only force acting down is going to be 1g newtons. But the upward force remains the same because the spring is still extended to the same position initially. Now this means that the resultant force is going to be 2g newtons because it's the difference between the two forces is 3 minus 1. So let's use the letter F to represent the resultant force. And that resultant force is also equal to the product of the mass and the acceleration, as we can see from Newton's second law. So rearranging to make acceleration the subject, because that's what we want to know, we can divide that 2g by 1 kilogram, which is the mass of the mass itself, which is going to be accelerating, and then we can find what that acceleration should be. So we end up with a value of 2g. Don't forget that that 2g is in meters per second squared. So the correct answer here will be C. An object falls freely from rest. After falling a distance d, its velocity is v. What is its velocity after it has fallen a distance 2d? Now for this question, we need an equation that relates the velocity of the object to the distance it's travelled. The one that I'm going to choose is v squared equals u squared plus 2as. And then here are the meanings of each of the symbols. So we're interested in how that final velocity changes as the displacement changes. Now we can make this equation a lot simpler. As you can see, I've highlighted there that it's falling from rest, so actually the initial velocity is going to be 0. On that basis, we can say that v squared equals 2as. And we can also say that v is equal to the square root of 2as. Now from this, you might be able to see already what the relationship between v and s will be, but it's effectively, if we double the value of s, which in this case we're calling d because it's the distance travelled or the displacement, what we can actually do is take that 2 out of that square root and place it on the front. Now we know that the square root of 2as is also equal to v, so we can say that actually when that distance is doubled, we end up with the velocity being multiplied by a factor of root 2. So the answer to this one is going to be D. An electric motor of input power 100 watts raises a mass of 10 kilograms vertically at a steady speed of 0.5 meters per second. What is the efficiency of the system? Now, for an efficiency question, let's write down the equation first of all. Now, interestingly, we can actually write the same equation using power instead of energy, as we're just eliminating a factor of time on the top and bottom of the equation. Now, we've got an input power already, so we just need to find a way of calculating an output power. Now, the equation which you can use, and it might be better to derive this one first of all, just so that you're reassured in your own mind how it works, is power is equal to force multiplied by velocity. And effectively, it comes from work done is equal to force times distance, and you're dividing both sides of the equation by time. And you can see on the right hand of that equation where I've got F times D over T. Well, D over T is just going to be speed, or if we're using displacement, then it's going to be velocity. So we would end up with force times velocity. And on the left hand side, power is equal to work done divided by time. Now we have a speed already, which is 0.5 meters per second. We just need to work out how to calculate a force. Now you can see that the mass of the object is 10 kilograms. Now the way to work out the force exerted in lifting that at a constant speed, well, we just multiply that mass by the gravitational field strength. So it would be 10 times 9.81. So all in all, to find the output power of this electric motor, we would multiply 10 by 9.81 by 0.5. Now, instead of calculating that, we're going to put that straight into the efficiency equation. So we're dividing it by 100, and that will give us our efficiency. And that should give us a value of 49%, which is approximately equal to 50%. So the answer for this question is going to be C. The velocity of a vehicle varies with time as shown by the following graph. Then we've got that diagram there. Which graph below represents how the resultant force F on the car varies during the same time? We've got 4 graphs here to choose from, each of them being force time graphs. Now, I think the question is trying to confuse you a little bit here by saying force time graphs, because that's not something that's typically covered in as much detail as something like displacement, velocity, or acceleration time graphs. But we're going to rely on what we know. The key point here to note is how they mentioned the resultant force F on the car. Now, from Newton's second law of motion, we can actually say that F is equal to ma. The resultant force is equal to mass times acceleration. And therefore, the acceleration is the resultant force divided by the mass. Now, on the basis that the mass of that car is not going to change throughout this motion, we can basically say that the acceleration is proportional to the resultant force. Now, what that means is that all of these graphs may as well be acceleration time graphs. You know, we could literally change this on all of them to say A. So we're interested in acceleration time graphs, really. Obviously, that graph will be stretched vertically by a factor of m or squeezed, but we'll ignore that. So analysing this graph, the original graph, first of all, we can actually see that the gradient of the graph is 0 at the beginning and 0 at the end. Now remember, the gradient of a velocity time graph is the acceleration. So we're looking for a graph where the acceleration is 0 at the beginning, but also 0 at the end. Now this does actually tell us the answer. The only graph here where the acceleration is 0 at the beginning and the end is going to be A. So A is the correct answer because the rest of them are not 0 at the beginning and end. But let's just look into this a little bit more. We can see that the acceleration, or the gradient of the original graph, is greatest at the middle. So what we should expect is that where that gradient is the highest at the middle, the acceleration of that car should be highest at the middle of its journey. Now, of these 4 graphs, the only graph, again, with a maximum at the middle of the journey is going to be A. So A is the correct answer. Which one of the following provides direct experimental evidence that light is a transverse wave motion rather than a longitudinal wave motion? Now we've got 4 options here, one of which distinguishes light as only a transverse wave motion and almost confirms that it's not a longitudinal motion. So let's go through each of these and see why they might be right or wrong. So for the first one, 2 light waves that are coherent can be made to interfere. Well, actually, this is a property that's true of any kind of wave that could be transverse or longitudinal. As long as they're coherent, they can interfere. If you look at 2 speakers, for example, if I just draw a quick diagram, as long as those 2 speakers are connected to the same source of signal, then they will emit coherent waves, and those coherent waves can interfere just as they would with a Young's double slit experiment for light. So actually A would be incorrect. Light can be diffracted. Well, actually longitudinal waves can be diffracted as well. If you think about sound traveling through a gap, such as a doorway, well, you can hear that sound if you were around the corner from wherever that source was being emitted. So it's perfectly possible for longitudinal waves to be diffracted as well. So diffraction isn't a distinguishing property between transverse and longitudinal waves. Light can be polarized. Now this one's interesting because actually polarization is something that can only occur in transverse waves, because polarization refers to the restriction of a wave into one plane of motion. And the only way it can move in a plane of motion is if it's oscillating perpendicular to the direction of travel of the motion in the first place. So let's just jot down the definition of a transverse wave. So where those oscillations are perpendicular, the direction of the wave and the oscillations form a plane. But actually where longitudinal waves oscillate parallel to the direction of wave motion, they only move in one dimension. So actually, if light can be polarized, that means that it must be transverse. So C would be correct. Now, just a quick note on why D would be incorrect. The intensity of light from a point source falls off inversely as the square of the distance from the source. Well, that's just the inverse square law, but described in more detail, and that will apply to any wave. The same would apply for sound. The intensity, which relates to the loudness of the sound, that falls off inversely as the square of the distance, just as it would do for the brightness of the light. So D would be incorrect as well. So correct answer, definitely C. A string passes through a smooth, thin tube. Masses m lowercase and m uppercase are attached to the ends of the string. The tube is moved so that the mass m travels in a horizontal circle of constant radius r and at constant speed v. Now, a point to note here actually is that it's a smooth, thin tube. By smooth, what they mean is that there's no friction between the string and the tube, so there are no additional forces there. And by thin, what they mean is that we may as well treat the radius of the tube as being 0, so that the start of the string, the other end to the small mass, lowercase m, is going to be at 0 radius. Which of the following expressions is equal to m? And then we've got 4 options here. They look relatively similar. You can see there are sort of m's and v squares and so on, and that hints at the equation for centripetal force. That's actually where we're going to make our first stop. So if we just quickly write down that equation for centripetal force, F equals mv squared over r. So if we look at this small mass here, the only force, if we're ignoring gravity, that's acting on that mass is the centripetal force that's keeping it in a constant circle. And you could argue that the source of that centripetal force is the tension in the string. Now that tension in the string is going to be equal to the tension in the string holding up the larger mass, capital M. If it's holding that mass at the same point vertically, then what that means is that the tension is going to be equal to M times G, or capital M times G. So if we bring these two expressions together, we end up with this expression here, and then all we need to do is divide both sides by G, the gravitational field strength, and that's the expression that we obtain for capital M. And as you can see here, that's the answer provided in option C. So C is the correct answer here. The frequency of a body moving with simple harmonic motion is doubled. If the amplitude remains the same, which of the following is also doubled? Now we've got four values here, some of which are going to relate to the amplitude and the frequency of the oscillating body. We just need to find which one is proportional and therefore will double alongside the frequency. So if we go through one by one and just find an equation that either proves or disproves that the frequency could double. So starting off with the time period, well, we know that the time period is going to be inversely proportional to the frequency, so it can't be that one. The time period will actually halve. The total energy, well, we can write down that that's equal to the maximum kinetic energy, because at one point in its motion, all of that energy of that body will be kinetic. So we can say that it's equal to a half times the mass times the maximum velocity squared. Now we're going to come back to that one because it's worth just working out what the maximum velocity is in terms of an equation that relates to frequency. So let's look at C. We know that the maximum velocity of an oscillating body is equal to omega times capital A, or the angular frequency multiplied by the amplitude. Now, since the angular frequency is actually the normal frequency multiplied by 2 pi, we can actually say here that Vmax and F are proportional. Because we're keeping the amplitude the same, doubling the frequency will also double the value of Vmax. Now let's just go through and discuss why B and D would be incorrect. Well, if we look back at B, we can see that the total energy is proportional to Vmax squared. Now, on that basis, if there's a squared relationship there, then actually the total energy is going to be also proportional to the frequency squared. So actually that would mean that doubling the frequency would quadruple the total energy, so it can't be that one. And then finally, the maximum acceleration. Well, if we write down one of the earlier equations that summarizes simple harmonic motion, what we can do is make some substitutions. First of all, by saying, like we said before, that omega is equal to 2 pi f. But then we can also say that A max, the maximum acceleration, is the acceleration that occurs when the oscillating body is at its most extreme point. So when that displacement is equal to the amplitude. And as you can see there, the maximum acceleration is also proportional to the frequency squared. So doubling the frequency would quadruple the maximum acceleration, so it can't be D either. So correct answer is C. A particle oscillates with undamped simple harmonic motion. The acceleration of the particle, 4 options here, is always in the opposite direction to its velocity, decreases as the potential energy increases, is proportional to the frequency, or is least when the speed is greatest. Now for this question, I think if we go through each of the possible answers and try and work out whether they're right or wrong, and then see if we can deduce the correct answer. So for option A, the acceleration of the particle is always in the opposite direction to its velocity. Well, let's think about that object moving with simple harmonic motion. For example, just an object moving from side to side. So this object will always be accelerating when it's not at the center, because the center is the only place where there is no net force on the object. So there's no resultant force and therefore no acceleration. So if we just take a point on this motion, doesn't matter for now where it is, but for example, just to the right of the center. So if you picture the particle moving back towards the center from the most extreme point, it's just been to the point on the far side, on the right, and it's now moving back towards the center. Anywhere on the right-hand side of that center point, there's going to be a resultant force acting towards the center, i.e. from right to left. And considering that that object is already moving from right to left, its acceleration must be in the same direction as its velocity. And that therefore disproves this idea that acceleration of the particle is always in the opposite direction to its velocity. So A cannot be correct. Option B, acceleration of the particle decreases as the potential energy increases. Well, what we're saying there is that the potential energy always increases the more the object moves away from the center. Again, if you picture it as being on some kind of spring system that's attached on both ends, there will be more potential energy the further away it is from the center. But in addition to that, it's got zero acceleration at the center and maximum acceleration at the outsides. So actually, I would argue that the potential energy is larger when the acceleration is larger. It's at its maximum at the extreme ends of its motion. So B is also incorrect. C, the acceleration of the particle is proportional to the frequency. Well, if we write down an equation that relates the acceleration to the frequency, now what I've included here is the angular frequency, which actually is proportional to the normal frequency, but let's substitute that in anyway. And as you can see there, the acceleration is proportional to the frequency squared. So actually there is no proportionality between acceleration and frequency. Now that would tell us that D is correct. But let's just confirm that the acceleration of the particle is least when the speed is greatest. Now, speed is the greatest at the center. That's just the nature of simple harmonic motion. The speed is the least when it's at the outsides, when it's actually brought to a stop in order to come back towards the middle. So the acceleration of the particle is going to be zero at the center, like I said before, because that's where there's no net force. If we write down Newton's second law of motion, which tells us that the resultant force is equal to the product of the mass and acceleration, if we rearrange that to make acceleration the subject, you can see there that the acceleration, provided that the mass of the object stays the same, the acceleration is proportional to the resultant force on that object. So actually at the center, where there's no resultant force, there's no acceleration. It's least when the speed is greatest, because the greatest speed is also at the center. So D is definitely correct.